Okay. Hello everyone. Uh, we organize these. We are hosting DevDay today. We organize these monthly events to talk about tech or the problems or the things that interest community in their day-to-day life or day-to-day work. So today we are going to talk about Java using virtual threads. Bhavesh is the speaker. He's been working with Sahaj since past 1 year, and he has almost 8 years of experience in the uh, domain that he is working in. So most of you must have heard about Java 21, right? So yeah, so this is the topic. Also, if you are interested in some topic that you have knowledge on and you want to share with some community, we'll be happy to host you. Just give us that talk detail. We'll make that happen. Okay. Okay. All right. Yes.
This will be part of the JVM.
Sorry.
This will be the part of the JVM.
Yes. This will be like first session in the JVM series. So there will be many more sessions on the JVM. But yeah, this is the first session on the JVM series. So stick along if you want to learn more on the JVMs.
Cool. We can get started. I think I'm audible to audience on online, basically. Am I?
Yeah.
Awesome. Okay. So hi everyone. As Vinayak mentioned, my name is Bhavesh. So today's talk is mostly on the virtual thread. Virtual thread is basically the Oracle guys has done a good job. In last 5 years, basically they have introduced this as part of Java 21, released it. The first introduction happened as part of Java 19. Then the second preview was released as part of Java 20, and now finally it is released. So we'll go over it and understand how we should use it. What are benefits of moving towards virtual thread? When should we use it and how it works internally? So yeah, this is the agenda for today's talk. We'll go through the need of concurrency, understand thread per request style, limitation of native threads, and then the ways to overcome limitations, and then discuss about Loom, virtual versus platform threads, how it works internally, adoption guide, and then at the end we can take the questions and feedback. Okay, need of concurrency. So can anyone tell me what is the need of concurrency? Maybe let's make this talk interactive, and you can also speak up if you have anything to say.
Yeah, to execute multiple tasks, right, at multiple times. So it's a kind of a worker model, right, whereas a task has to be done with parallel things. Say suppose it's to be done by threads, right? Yeah.
But what is the need of executing things parallelly?
So it will reduce the execution time, right? If it is taking 10 minutes, if you are using concurrency, there are chances that it will take some 5 minutes or something like that. Basically, time optimization. Yeah.
Right. So one thing is to utilize the CPU properly. We don't want CPU to be idle. And as you mentioned, that to fulfill the need of modern application, we mostly know that the modern application requires high throughput on low latency. And today we are going to target high throughput in this talk. Okay, let's take this talk with the one example of thread per request style. So thread per request style model basically talks about assigning one thread for request. This is mostly your typical web application works this way. Whenever you get any request, you will assign one thread for that particular entire request, and then that particular request will be responsible to execute entirely, right? So here we have one API called recommend products, basically one method where we are passing one customer ID, and this particular API returns the product recommended for that customer. Here we are doing 3 operations. One is we are getting the customer, we are fetching the customer preference, we are fetching the orders, and then we are preparing the recommendation and then returning it. If there is nothing to return, then we are returning the empty list. Anyone wants to talk about what are the pros and cons you can see when you look at the code? Anything that you find that, okay, this is good, something which you find weird, some scaling issues? Okay. So if we talk about good part, you can see that this code is simple enough to understand, right? Simple enough to reason about, because you know the flow goes from top to bottom. You first you're fetching the customer, then you're fetching the customer preference, order service, and then the preparing the product recommendation. So for example, something goes wrong in any of those particular call that we are making, you know that the flow will be stopped at that point of time. Also, it is easier to test and easier to read, right? Uh, but do you think this is scalable code? I'll tell you, for example, let's say this fetch customer service, and this all three calls which we are doing is an external call. So we are calling the other service to fetch the customer detail. We are calling some other service to fetch the customer preference, and finally fetch the order history. So assume that order history takes 1 second to get the response. The customer preference takes around 500 milliseconds, and this takes around 400 milliseconds. And we just require only 50 milliseconds in order to prepare the product recommendation. So entirely we are waiting for 1.95 seconds to return the response, right? Any answer, like how can we improve this?
We use future or something.
Okay.
Like
Okay. So, and what is the problem with this code? So thread per request style basically governs by little law. So little laws tells that, okay, a throughput is basically your behaves from in terms of number of concurrency divided by latency. So for example, let's say if you have 10 concurrent requests, which is being processed in 50 milliseconds, it means your application is able to process 200 requests per second, right? If you want to increase throughput, then what are the ways? Either you need to increase the number of concurrent requests that you can support, or you need to decrease the latency. Now, for example, if we talk about the external calls, the latency is not in your hand. You might not be able to change the latency because it's somebody else's service and you don't have control over it. So one way to increase the request is by basically increasing the or supporting the number of concurrent requests, right? So for example, if you have to support 100 requests, if you have to increase the throughput to 2000 requests per second, you need at least 100 concurrent requests need to be supported here. If you want to increase to 20,000, it will go to 10,000. If you increase more and go to 1 million or 2 million requests per second, it means you need 100,000 requests to be supported concurrently. Now, what's the problem with that? So the limitation, can we do that? Like, can we create 100,000 threads? Because we said that, okay, the in thread per request style, we assign one thread to process the entire request. So when we are saying that we need to, if we want to increase the throughput of that application, at least we need to have those many number of threads created, and they need to serve the request. So you guys might know that creating those many threads are not practical. And the reason is basically the limitation of platform threads. So JVM, so currently the native threads that we are having, those threads are basically thin wrapper around the kernel or the OS thread. So whatever you assign to those particular JVM thread is basically being handed over to the kernel thread, and kernel thread performs the operation. So if there is any blocking call, it means your kernel thread is going to be blocked, right? Also, the threads basically, when you create a thread, so typically on x64 machines, it takes 1 MB of size, stack size, and on x86 machine, it takes around 512 KB of stack size. So for example, if you are creating millions or 100,000 threads, imagine the size that you require in order to create those number of threads, right? Then that's only the stack size. Then you have the heap size as well. So you need a massive machine to at least support it. Then the high memory okay, the thread creation is also expensive. It's just okay. For example, let's say for some reason you are able to create 1,000 or 100,000 threads, but the time it takes to create a thread is also a heavy operation. Also the context switching, right? So when you have to switch, there's many threads, the time it takes is huge. So that's why we cannot create. So that's why like we don't have option to create as many threads as we want. So what are the ways to solve these things? So people has come up with the ideas of, for example, creating a thread pool. So in thread pool, what you typically do is you create some amount of threads. For example, Tomcat creates 200 threads by default, and then you create number of tasks and assign those tasks to those thread pools. So then thread pool basically assign whichever thread is available, it will pick up any task from the queue and start processing it. But now what's the problem with the thread pooling? So in thread pooling, you only have the limited number of threads. So for example, if you have 200 threads, so at a time, and if your task is a blocking task, right? You are making a call, which is like external call, and it is basically a blocking call. Then what happens is 200 threads, let's say even in from the 200 threads, if 30 or 40 threads are blocked, it means you're wasting some CPU. Because those threads are blocked, it cannot perform anything else. And if let's say all the 200 threads are blocked, and if you have massive load, then in that case, basically your service will not perform well. So those are the scaling issues that we see with the thread pooling. So then what is the solution? So as you mentioned that, okay, we can also use the completable future of future, basically asynchronous way of handling things. So there are two things we can do in terms of asynchronous style. So earlier we used to do async blocking. What is async blocking? So for example, we had this particular flow of the execution. So we were fetching the order, then the customer preference or the customer, and they were taking basically this amount of time, 1 second, 5 milliseconds, 400 milliseconds, and then the 50 milliseconds. So in total, it was taking 1.95 milliseconds. So if you want to improve it, one way to do is basically you call fetch order, and parallelly you call fetch customer preference and the fetch customer. So here, while the fetch order is in progress, you will be able to fetch the other two things and then construct the response. So in total, it goes around 1.05 seconds. Here you are, when you are saying async blocking, what it means is you are creating 3 different threads or assigning this task to 3 different threads to fetch this data and then construct the response, right? So essentially, here you have better approach, but still you are blocked for that particular time, and you are wasting some of the CPU there. So if we, then the next thing that we can, okay, the solution for or the optimization that happened on top of this is coming up with the non-blocking stack. So then people has come up with the non-blocking stack. You might know, for example, Java has introduced NIO stack. Similarly, there are many other languages which are using the non-blocking stack. Non-blocking stack is basically when what we are doing in non-blocking is your request or your thread itself is not blocked. What it means is whenever the fetch order request is made, the request will be unblocked immediately, and the call will be given to the channels or the channels to process or take it forward. So basically, there is one thread or some thread basically which are making that call, but your framework threads are not blocked. What it means is that it's mostly now event-based communication. So whenever you get a request, your thread makes that call, and then immediately it gets freed. Similarly, when we are making this call, that thread will again make a call, and immediately it will be freed, and then we'll wait, we'll do some other operation. So that is asynchronous non-blocking way of handling things. So here, if you are having millions or 100 or thousands of threads, basically your thread pool will able to handle those requests. What it will do is it will basically pick one request. If there is any asynchronous or any blocking call, it will call that particular thing and immediately free up, and then we'll be able to process the other request. So that is asynchronous non-blocking. But okay, this comes with its own challenges. People had to develop this non-blocking not because it's easy, but as we face, there is an issue with, or there are challenges with the synchronous way of doing things. When you're blocking, you are not able to scale up properly. And that's why people had to develop this non-blocking stack around with yeah. So when you look at the code, right? So what are the challenges? So challenges are, one is it's no longer simpler. So when you read a code, it is not, when you look at the non-blocking code, basically you might have seen the completable feature code where you are doing or composing things. So it is not that simple to understand to or read or to reason about. For example, if these three things are going or happening in parallel, what if something goes wrong in customer preference? Will it terminate the execution here, or the fetch customer call will go on? Also, it will be hard to understand the what is the stack trace. When you like take a thread down, you will not get the usable context around the stack traces. Debugging and profiling become hard. So when you try to debug or even you test it, it becomes harder than the synchronous code that we saw. So essentially, the application unit of concurrency is no longer platform's unit of concurrency. So the reasoning of code becomes harder when you move to the non-blocking stack. So to solve the problem of asynchronous, or basically to solve the problem of synchronous way of doing things, for example, scaling issue, and to help to make your code look same as the synchronous code, the virtual thread has done a good job there. So here what has happened is, so virtual thread is basically nothing but your user defined threads. So for example, you can see here, so these threads will be created within the JVM, and these threads are mapped onto your platform threads. So it's now responsibility, or it basically JVM is in control of creation and scheduling of these threads onto a platform threads. Here it is not one-to-one mapping, but rather one thread can be mapped onto any of this platform thread, which is also called as a carrier thread. And then those particular threads are being again executed. For example, these are nothing but the kernel thread. So one benefit here is it's cheap to create. What it means is only few bytes, 100 bytes basically are required in order to create this particular virtual thread. So you can theoretically create infinite number of virtual threads because it's not taking that much amount of memory. Also, it's very fast to create. JVM handles the lifecycle and scheduling. Because JVM handles the lifecycle and scheduling, JVM has more control over scheduling part. JVM can schedule it or unschedule it, or park it or unpark it based on the blocking call that is happening. User thread per request style more efficiently. So now you can use the thread per request style code which we saw, which is simple enough to understand, write, and test with the same performance as the asynchronous way of doing things. Can achieve same scale as a asynchronous code. Does not require learning new concept. This is again one benefit is if you are moving to virtual thread, you don't require to learn new concept like you have to learn it for reactive stack or the asynchronous stack. Okay, so let's understand how we can create this virtual thread. So there is executor service, which is introduced as part of executors itself. So new virtual thread per task executor. What it does is basically it creates new virtual thread every time you submit some task to that executor. So here we are saying that, okay, for 0 to 1000, for each iteration, we are creating a new thread and just giving this duration of sleep of 1 second. You can run this as well. It works really well. We can now check the code. You guys are able to see the screen, right?
Yeah.
Okay. So if you see, the same code is here, recommend products. We have again fetch customer preference, order history. So if you want to, so this is basically your typical Spring Boot application. So if you want to enable or use virtual thread on your existing Spring Boot application, So if you are using Spring Boot before 3.1.3.2.x, then okay, let me open. All you need to do is you need to create this beans and override the existing executor for the Tomcat. So here you can say set executor and you can say executor.new virtual thread per task executor. Also, you are doing the same thing for the async task executor. You are giving the basically giving the new executor for the virtual thread. How we are doing here is basically we have added this property called thread executor virtual. So if it is virtual, then we are creating a bean, which will be used in order to replace your underlying executor service with the virtual threads. No, you need only one. So if you are only using the synchronous code, then only one. But in case of async, any async operation, right, you need both. So it is recommended to do to override for both the protocol.
This case, the Tomcat threads will basically be the
Virtual threads, yes. So Tomcat now will use the executor, the virtual thread pull executor service. Okay. So now you were saying that okay, it's gives the same kind of throughput or scale as async programming does, but do we have any proof? So well, let's look at it. Okay, just give me a second. I will just. So what I'm doing is I am starting this application. Again, I have commented out this property. So now the underlying thread pool would be the normal platform threads that Tomcat uses. And here we have, if you see, we have test. Here what we are doing is, we will first start with the 100 threads. As Tomcat has like 200 default thread in the thread pool. So we are going with the 100 thread at are you able to, okay, I think. Okay, I am not able to zoom here. Give me a minute. Okay, it's to zoom. Okay, I will just explain if you are not able to say it. So we have 100 user. So we have given that okay, 100 parallel user is to access this particular endpoint. For 30 seconds, we will run this test. So we have created this endpoint. So endpoint is the same which we saw. Here basically, okay, let me open. So product recommendation service. So what we have done here is nothing but we have induced some kind of sleep here just to simulate our experience for blocking part. So if you see here, 500 millisecond of sleep is there, 400 millisecond, and then the 1 second. So in total, it should take more than 1.9 second. And then we are basically calling that endpoint 100 times with the 100 concurrent request. Okay, let's run this. Cool. So if you see, then the request would start now. We can see there are requests being made every second. And if you look at the sample time, which is below 2 seconds, are you guys able to see properly? No. Now. So if you see, the request time is basically within 2 seconds because we are only in querying 100. I mean, sending 100 request 200 requests per second. So if we look at the response graph, it's a constant time, right? It didn't go up above the 200 seconds. Now let's do one thing. let's say we are increasing our request to 1000 requests per seconds. And let's see what would be the, okay, nice. So you can see the request has increased, but if you look at the time that it takes to process those requests, right, has increased as well. Latency. So it means your application is not able to handle that load. Yes. Because your request is basically waiting, your threads are waiting on those blocking part. So the new requests which are coming are skewed. And that's why it's taking a long time to process your request. So after 30 seconds, if you look at the graph, you can see the requests are going on and the time is increasing. If you look at the response graph, it's basically going up, right? So this is the problem with the threads, the platform threads. Now let's test it out with our virtual threads. So I'll go here, uncomment it out, and then run the application again. Here we'll clear the graph. So you have seen graph, right? So basically here it started with 6 seconds. The reason here is basically because of the contention. So as it supports only 200 requests per request at a time, we are giving 1000 requests. And because of those requests, there is a contention, and that's why it takes a longer time to process or to complete your request. So we can clear this. The application is up. And with the same load, here we are keeping the same load, 1000 requests per second. And we are running for the 30 seconds. And if you look at the response, it is constant within that 2 seconds. Same load, we saw earlier that it was taking a lot of time, but now as we move to virtual threads, it is within the time limit that we were thinking that, okay, it should take around 1.9 seconds, not more than that. Right? So after 30 seconds, if we look at the graph, it is constant. Same code, yes. We just changed the underlying executor service. We are saying that rather than using platform threads, we want to use now virtual threads. Yes. Awesome. Any question here, or we can go next?
In this case, why is there a downward trend? Or
So it
is
started
just
with the 1000 request, but then it was able to catch up the load, and then has it gone down. So when you start, right, you create the threads, right? Basically, you need to create virtual threads. So thread creation is also takes some time, and that's why it's more than 1.9 seconds. As you have many threads, it's already started to process it. Once it is created, being in use, then it goes down.
Okay.
Cool. So we saw the performance as well. Now let's understand how it is implemented or how it works internally. Right. So basically, virtual thread are again implementation of Java lang.thread. So everything or all the observability, or if you say monitoring tools which are there, will also be useful or work for the virtual threads. You can take the thread dump and you can also monitor it. All the support is also provided for the virtual threads. There are two main constructs to understand here: continuation and scheduler. So continuation is basically again low-level API which Java doesn't, the Oracle doesn't recommend to use in production. So, but they are using the continuation in order to achieve this. And then there is a scheduler which schedules the threads or the task on the platform thread. So what happens is, when you assign or when you give any task to a virtual thread will wrap that particular task within a continuation, and then and then the task will be given to the scheduler. So here by default, fork join pool is being used for the scheduling part. So for here, as we see, in terms of fork join pool, it uses the default parallelism is equal to number of your hardware threads. For example, the virtual thread is being carried on the worker one. So now what happens is whenever there is a blocking call, the continuation.yield will be called. So this guys have changed. It's not that simple. So for example, this guys has added or changed the existing Java code in order to understand the blocking calls. So whenever JVM finds any blocking call, it calls the yield method, which essentially puts your virtual thread, which is nothing but an object, on your heap. So virtual thread basically contains all the context it was running on. So let's say you were running some instruction, and at some instruction you are calling the blocking code. At that time, basically that particular instruction is also saved with the context. So whenever there is a data available, so what operating system does is whenever there is a data available, it basically gives a signal to your JVM, which internally interrupts or calls the continuation.run method. Continuation run method is nothing, again, it runs or it assigns that virtual thread to the worker thread. So for example, if the same thread was available, then the same thread will be able to carry the virtual thread. But let's say the worker one is busy in some other task, then the virtual thread can be assigned on the worker two. So the virtual thread can be carried by any of the worker threads, because as it has the context where it left earlier, it can continue its own work. So that is how it works internally. Any questions? So what happens essentially is, even though your code looks synchronous, but underneath, whenever there is a synchronous or blocking call that JVM finds, it replaces that synchronous call with async stack or non-blocking stack. So then there is a poller which basically polls this particular non-blocking operation, and once it gets the result, then it's basically assigned that virtual thread back to the or task basically back to your worker, any of the worker thread, and then it can continue from there. So this is how it works internally. We now can discuss about the adoption guide. Any question so far?
So what will be the worker pool size there in the fork join pool?
So by default, it is basically same as your underneath hardware threads. For example, if you are using 4 cores, it is 4, but then it can also grow in size. You can also configure it.
Okay.
So one more thing, I mean, if there are a lot of blocking virtual threads, then they would fill up the chances are that they would fill up the heap. Since
right. So virtual thread so the size of virtual threads are very small. So one essential thing is whenever you create a virtual thread, try to make sure that your task which you are creating is small enough so it will just complete that task and then die off. So once that virtual thread is die off, your garbage collector will clean it.
Okay.
Yeah.
Okay. Any recommended time or something for a task to be given to a virtual thread?
No, so it basically depends on your use case. Ideally, you should, let's say if you're using, if you are having any non-blocking call or blocking call, then in that case, you need to make sure what time it takes to complete the task, right? Even though the blocking code is fine, but if you are handling a lot of things in one particular task, right, which can grow, for example, you're adding a lot of creating a big objects within that particular task itself, which can grow indefinitely, then it's basically can create a indefinite of we will also talk about it, like how we can avoid it. But we need to make sure that we are giving small tasks so that it can die off and then clean regularly.
Okay. Also, one more thing, what I understood from virtual threads is it is another layer above the JVM threads. So, right. So
Yeah.
virtual threads would be given to the JVM threads, and JVM would give to the platform threads. So it's kind of an another layer. So
Yeah.
I'm not able to understand that how it is reducing the overall time, since it's another layer and it's being, I mean, I understand that it's the concept can be that I take a lot of tasks in a queue and
Mhm.
then just return back, but the task or is there in a queue, and then I keep pulling, kind of a concept, but I'm not able to understand that internally. Maybe there would be some kind of an implementation detail that even though adding another layer to the JVM threads, it's still able to reduce the time. So that is what I'm not able to understand yet.
Okay, so as we saw, what are the ways to increase your concurrent request or support the
Yeah,
concurrent, right? One
agreed.
is either you have like infinite number of threads. So for
Hmm,
each particular request, you assign a thread, and then that thread will be responsible to perform the complete request, right?
agreed. Yeah.
But now your platform threads are having issues of, as we saw, that basically the memory footprint is high, the thread
Yeah.
creation is high, time that it takes to create a thread is high, the context switch that happens is very high, and that's
Hmm.
why it is not we cannot create
Okay.
as many threads as we want, and that's why OS also has some capping over it, right?
Okay.
But in terms of virtual thread, now as it is kind of an object, simple object,
Hmm.
so JVM can create 100 of those small objects to uh, accept that request that you are sending to your application. So now
Okay.
rather than your threads or the platform threads which are going to accept the request directly, the first it will go to virtual thread,
Yeah.
and
Okay.
virtual thread will handle it. If it say, and if it sees that okay, the request is basically spending a lot of time in the blocking calls, right?
Hmm.
At that
Yeah.
time, it will say, okay, I am blocked. It will ask virtual the JVM that okay, I am blocked, and now you can assign any other or assign the underlying worker thread to
Hmm.
perform some other task. So in that case, what we are doing is we are yielding. So the virtual thread is basically yielding, and then it basically parked on the heap
Hmm. Okay.
till the time it gets the data. Once the operating system sees that there is a data which was requested by this particular task, it will again put onto the worker thread. So in
Okay.
that way, your underlying worker threads are not blocked. So,
Hmm.
for
Okay.
example, let's say if you have a thread pool of 200, so those 200 threads are not blocked. They are able to perform, or they are able to take new task and work on it.
Yeah. So, but the limitation of the platform, I mean, JVM threads routing to platform threads, that is still there. So,
Yes.
if the platform thread is blocked and virtual threads, they need to, give to the JVM thread. So, and then if the platform threads is anyways blocked, the virtual thread will still be stuck, right?
Right, right.
Am
So
I
that we'll
understanding
discuss
correct?
again in the adoption guide. So when we
Okay.
discuss about the adoption guide, we will also discuss like how we should adopt to it, when we should use it, and
Okay.
what cases it will give the benefit when we use the virtual threads.
Okay.
Hey, sorry to interrupt. Is the session going to be recorded? Like, I need to leave the session. So,
Yeah, it will be streamed and also will put it on YouTube.
okay, thank you.
Yeah, thanks. Okay, so let's discuss about the adoption guide. So basically, it is recommended to use your normal blocking way of doing or handling the things. For example, here it is recommended to use thread per request style. What it means, your one thread will be using or one thread will be assigned to perform the your operation. For example, here rather than going or using the completable feature, because here then you are creating some different threads and handling or doing this operation within it. So benefit, you will not get that benefit for here because it's already in a synchronous way. So you will get benefit or see the benefit of when you write your code in thread per request style. Then never pull a virtual thread. So one recommendation is you should not pull a virtual thread. So as platform threads are scarce resource, so it makes sense to pool those particular threads, and that's why we pool platform threads. But as virtual threads are very cheap to create and infinitely plentiful, you should not pool it, or you should not have a pool of virtual threads. The other reason is, if you start pooling it and if you are creating a millions of virtual thread, then your heap will keep on growing, because then you are not removing those threads, or those threads are basically being used, and that's why it will never die off. Though, so when you say new virtual thread per request task executor, even though it's a in normal task executor or normal executor service that you might have seen, there mostly your creates the pool executor with the size of some threads. So basically it pools the thread, but here it will every time when we submit a task to this executor, it will create a new virtual thread and assign that particular task to that virtual thread. But what if you want to limit the concurrency? For example, if you have some use case where you want to do a rate limiting or limit the concurrency, so in that case, you can use some OS level construct like semaphore. So semaphore, basically here we are saying that, okay, only 10 concurrent requests we want to allow for this particular call limited service. So here you can first acquire, then you call the service which you need to do a limiting, and then you release the semaphore. So at a time, only 10 concurrent requests will be allowed to process or call this particular endpoint or service or API. So that is one way to handle it. And now here it is mentioned that don't cache expensive reusable objects. So if you so thread local basically works for virtual thread as well. So, but it is recommended not to cache those expensive objects. The reason is, here you can create infinite number of threads, right? Every time you create a new thread, the thread will also create a thread local. For example, if you are using the expensive objects within it, if you are caching it, then it will also be there in the heap. So your basically memory will die off. You will get the out of memory issues, or you need to have like a big memory there. So it is recommended not to use the expensive or not to cache expensive objects. So here in this case, there is a new concept called scope variable that is going to be released. So that is the scope variable is there as part of preview. You can take a look at it, how it handles this, or how it basically provides the value or provides the cacheable objects to your virtual threads. And then avoid lengthy and frequent pinning. So caveat of using virtual threads, there are two caveats. One is, if you're, let's say, within a virtual thread, if you're making a native call, then a virtual thread will be pinned onto your underlying platform thread, because now JVM has no context what is happening in your foreign function or in your native function. Even if there is a blocking call or non-blocking call, JVM will have not any understanding of that. So that's why it is not able to unblock, it is not able to park your virtual thread whenever there is a native or the foreign function call. Second caveat is the synchronized block. So whenever you are using a synchronized block, your virtual thread is basically pinned onto your platform thread. So if your synchronized block is just guarding some kind of a in-memory object, then it is fine. Even if your synchronized block is not making kind of a frequent blocking call or long blocking calls, which is still fine. But if it is like lengthy and the frequent blocking calls, and if you are using virtual threads, then it will be pinned onto your platform threads, and there you can see some scaling issue. So what's the solution here? So in this case, you can use the reentrant lock. You can just say lock create a object of reentrant lock, acquire it, perform whatever the operation you want to perform, and you can unlock it. So this is the current caveat. However, they are working on it to maybe, not sure, maybe in future release we don't see this issue, but this is the currently the pinning issue that we have. Okay, and the sixth thing is it is meant for the IO intensive application. Now, as someone was mentioning, what will happen? So this is only give you benefit when you have like IO intensive application, and this IO intensive application basically means that your application is doing blocking calls external blocking calls, be it database, network calls, file write, anything. But if you're doing some in-memory calls, right? Or if you're there is like a CPU intensive task, then it is not recommended to use virtual thread. You can just use your platform threads and then be done with it. Also, it's like virtual threads are not faster than the platform threads, but just the way it handles is optimized than the platform threads. So don't use for the CPU intensive application, and don't use in parallel stream. You should not make any external call actually in the parallel stream, but just calling it out. So yeah, that's mostly it. Any questions so far? Audience, guys online, if you have any question, you can ask.
So one question, right? So you said should not cache any expensive object. So and also you said thread local we can use in a virtual thread. So what kind of so usually we will cache simple date format kind of things, right? So those things can be cached, right?
So simple date format, the problem with it is basically it's very expensive object. Rather, you can go with the datetime formatter in place, which is kind of a lightweight object in place of the simple date format. Also, you can use the scope variable. You can also read about the scope variable, but scope variable is a way to provide. So what it does is just like the thread local. Thread local gives, so basically thread local provides the objects for all the threads which is being used, right? Similarly, you can also use a scope variable which gives the access to those kind of objects which are required for multiple threads. So that's the solution for it, or that's the alternative, a better way to cache the objects.
Got it.
Here there are more couple of reference link that I have put it here. You can go over this one. So it basically talks about the Loom proposal, the second preview, the documentation for the Loom, detailed notes like what all things has happened, or what all things are going on in terms of Loom and the scope variable that we discussed, structure concurrency. And then you can also read about the Spring Boot adoption. After Spring Boot 3.2.0, Spring Boot is adopting to virtual thread. So there is only one flag that you need to just enable, property, and then it will start using the virtual thread underneath. All Loom related blog. You can also read about this 1 million concurrent connection. And then there is a GitHub link for this particular demo. We'll put it on the YouTube as well for in the pinned comment, so you guys can take a look. Cool. If no question, then we can.
Bhavesh, I have one question regarding parallel stream. You mentioned that we should not be using it. Can you explain more on that?
So parallel
Why?
stream basically, okay. So parallel stream, if you are using virtual threads, right? So those are parallel stream. What it does is basically use the thread pool, and when it calls the so virtual threads is something which makes the external call, right? So you mostly use virtual thread in order to do a blocking operation. And if you are making a blocking operation, then it takes it need to understand, because it's already understands the async way of handling things. So if you're using within the parallel stream, it will not be beneficial. You can also read about the parallel stream not using the any kind of external call, or the doing things which is required to call the your external services. I can put a link over here because it's like a big
Yeah.
question.
Okay. Okay. Thank you.
Thanks.
I have one question. When your second example, when we second ran the execution, so how many platform threads it
200.
how many
200.
200
Yes. So the question was how many platform thread was used when we ran the virtual thread example, like when we started to use virtual threads. So by default underneath Tomcat, uses 200. But yeah, we can verify that, but it should be around that only.
When we don't use virtual thread, how many threads are created? Same.
Yeah, so default thread pool size is 200. You can also configure it. So that's not the issue.
Got
Bhavesh,
Sorry, hello? Hello? I think I lost you. Uh,
are you able to hear me?
yes, can hear you now.
I was asking, has virtual threads been adapted? I mean, you have any production ready code which is using virtual threads, or it's too new,
So
maybe?
we have mostly experimenting and using code which is not in like production, but we are planning to do it this week.
Okay.
Yeah.
Got it.
So we already had adopted the Java 21
Okay.
in couple of project which I'm like working personally, but in terms of production ready, we'll going to do it this week.
Okay. Okay. Got it. Thank you.
Cool. I think if no more question, then we can close the call. Okay. So just one announcement. So we are organizing the 50th Dev Day. It's gonna be our mega Dev Day. We are targeting the LLM related topics to discuss on the that mega Dev Day. It's gonna be a one-day event. So if you are interested, you can also register, or basically it is there on the meetup. So feel free to register for it. Cool guys. I really appreciate you joined. Thank you so much for joining.
Thank you.
Thanks.